Matter sometimes behaves as a wave and at other times as particles. It cannot behave as both at the same time. That actually led to two theories of matter, the wave theory and the particle theory. We're going to start a series where we'll deal with those theories one after the other. So stay tuned. For the wave nature of matter, it was like established via an experiment. You have a heated filament, you have it right there on the screen, and then a beam of electrons is emitted from that heated filament, and that beam actually impinged on a layer of metal film, or it could be a crystal. Either way, coming out of the metal film, the electrons were actually diffracted. When we say diffraction, we mean one source. It's more like the white light prism experiment, where you have white light diffracted into red, orange, yellow, green, blue, and all of that, which you have under light waves. All right, and it was the same thing with electrons here. So, and you have the rings, the diffraction rings, that's what we call it on the photographic plate. When you have a voltage V, and you know what voltage does, what potential difference does, it provides the energy necessary for you to have a complete circuit and your current and every other thing in move. So if you increase the voltage on the anode, the electrons would increase their speed, or we can say that the velocity of the electrons will increase, right? So when you increase the potential difference on the anode, then the velocity of the electrons will be increased. And that was what Davidson and Germer, that was what they noticed. All right, and then once that happens, the rings you have on the screen, the diffraction rings you have on the screen, will become much more smaller. The rings you have on the screen, the diffraction patterns, the diffraction rings, the electron rings, whatever you call it, will become narrower. So if you increase the velocity, the diffraction rings will become narrower. And if you're to take that to the other side, it also means or implies that the wavelength will decrease. So if you increase the electron velocity, the wavelength of the electron will decrease. Will increase the velocity of the electrons, and then the wavelength of the electron waves will decrease. That's an inverse proportion, and that is also shown on the equation you have on the screen. We have lambda, which is wavelength, equals Planck's constant, that's h. Planck's constant has a value of 6.63 times 10 raised to the power of minus 34 joules per second. So the wavelength equals the Planck's constant over the momentum of the object. All right, that's mass times velocity. That gives you the momentum of the object.